This session will be recorded, so I've already enabled the recorder. Wish to thank everybody for joining us on this webinar today. We hosted a webinar just recent about what was all the new implementations on Eagle.4. We just hosted that last Tuesday. So today we're going to actually show you a little snapshot that summarizes all the information that covered. But we're not going to go through this snapshot because it's just way too much information. We want to mainly concentrate only on what we're going to be covering today, which is going to be SPICE simulation. Jorge is going to be providing us all the details about simulation, as well as connecting to third-party simulators and having to recreate your circuit from scratch or over. Design an Eagle, simulate an Eagle. For those of you new to electronic design, SPICE or simulation program with integrated circuit emphasis allows you to check the integrity of your circuitry and predict the circuit behavior. In other words, all of those connected components in your schematic going to produce an output waveform that looks like what you expected. So you could use space simulation for a ton of use cases, like knowing what's happening with your voltage in your circuit at a specific point in time. The integrated SPICE simulation in Autodesk Eagle 8.4 comes with 3 modes: transient analysis, as well as DC AC sweep, and operating point. Now, I'm going to go ahead and give the floor to Jorge Garcia, which he's going to be sharing his screen. And also today, joining us is Ed Pataki from our development team, which was actually the person that implemented the simulation tool within Eagle. So we'll go ahead and join us. Jorge. And let me find Pataki and myself will be manning the chats. So if you have any questions throughout the presentation, we'll field them directly on the chat, or we will just ask Jorge to set up that example again. That way we could review your question as well. Okay, Jorge.
Cool. So, hi everyone. My name is Jorge Garcia, I'm a product support specialist with Eagle, and in this video, in this webinar, we want to show you how the new SPICE simulation is integrated into Eagle and how it works. So, right now we're looking at Eagle, the latest release, and what we're going to do is we're going to go to examples and GSpice. Okay, and GSpice is the underlying SPICE engine that's powering all of the simulation capabilities in Eagle. And this is one of the examples that come with Eagle now. We have several that really highlight all of the different features that you can expect to see in the integrated simulation. So to start, I'm going to pick something that generally can give you a pretty interesting result, something more than just a straight voltage. And it's a very simple little oscillator circuit. This oscillator circuit consists of 2 BJTs. As you can see, it's low parts count. It oscillates at about 100 kilohertz as indicated. And really, the bulk of what simulation is in Eagle can be described by this toolbar and the ngSpice simulation library that we'll be checking out shortly. Okay, so all of the settings, all of the probes, everything can be obtained from this top toolbar. So as you can see, this schematic already has several probes. We can add more using the probe command over here for voltage probe. Okay, we can also add phase probes. Now, the question may arise, do we have current probes? We can measure current in Eagle simulation currently. It's done by going to ngSpice simulation, which is a library that's new shipping with Eagle. And in there, I'm going to show you the object that you use to measure current.
I was going to make that a question, Jorge. You took it away from me.
I'm sorry. Didn't mean to. So we expand the library, and you'll see there's an ammeter device. So what you'll do is you'll place that within one of the loops of your circuit, and that'll allow you to measure current. So go ahead and say, I'm not going to place it right now. Let's go ahead and go to this icon, which is the Simulate Setup icon. Now what you're going to notice here are the main types of simulation. We currently support 4: operating point, DC sweep, AC sweep, and transient simulations. On the right, you'll see the simulator options. Most of the time, you won't have to adjust these. These control the convergence and the number of iterations that the the engine will go through a try to achieve a result. Depending on the models and the specifics of a given simulation, on some occasion you may have to alter these, but in general these settings are good for default, and for most of the simulations that you'll run into, you won't have to tamper with these. The only noteworthy thing here that I would like to mention is the R-shunt option. So in certain simulations, in order to achieve a DC point, you may have to turn R-shunt on. And we'll discuss a little bit more why later, but for now, suffice to say, if you see that initially you're having trouble or the simulator pops up an error that it can't connect a certain node or something like that, it's worth a shot to try to activate R-shunt. Later on, we'll show more specifically where this comes into play. Okay, so for now, this is our transient simulation. The other tabs in this window are netlists. This is a SPICE netlist for our design. So you can review it, you can check to see if there's any issues. Simulator output will show all of the numerical values once the simulation is run, and plot is self-explanatory. So I'll go ahead and click Simulate. Again, as I mentioned at the beginning, if there's any questions, please feel free.
So you're doing a transient simulation right now?
This is a transient simulation, so we see how the circuit evolves over time.
All right, it's over time, okay.
So I put in a whole bunch of probes, so right now there's a lot of extra stuff in here that it doesn't make it super clear what this circuit does. So what we can do is we can click on Select Signal, and we can eliminate, we can turn off some of these signals. So I'm going to turn off this one. That way we just see the output of the circuit. Okay, VN we know is a DC. I'll hit Apply Voltage, Apply Changes, sorry. And you guys can see this is a very, very good square wave oscillator. Okay, if ever you want to get back the original screen, because for example you zoomed in, you can click and drag to zoom in on any part of the circuit. You can click vertically as well as horizontally to zoom into different parts. Just click refresh and it takes you back to the original setup. As you can see, and as is more useful in Bode plot type analysis and AC sweeps, we can change the axes to be in log, both the X and the Y, and we can display decibels. Like I said, the simulator output contains all of the data that we see in the plot window. So this, if for whatever reason you wanted to take this data somewhere else for analysis, like a spreadsheet or something, you could copy it directly from here. Okay, in other analyses, you will see other pieces of information that may be helpful here. For example, in operating point analysis, you won't see anything in plot, but you'll see the results here in simulator output. So this is a basic transient simulation. Let's go ahead and show another type. So I'm going to go ahead and close this one. Not going to save it. And let's talk about operating point. This is the one that Circuits 1 students are probably going to be the most interested in. Okay, so it's a very simple circuit. It's one loop. Okay, and what we can do is we can go to Simulate, and notice that it has an operating point simulation. Operating point is basically your normal KCL, KVL type analysis. It gives you all of the voltages and all of the currents in every loop and every node of your circuit. So we're going to go ahead. We're going to go ahead and click Simulate. And in this case, there's no plot because you're just getting fixed values. But here in the simulator output, you can verify the results. So now if we look over here, we'll see that Eagle actually draws the different values at each node, and we get the current coming out of and into our sources. And we can turn this off using this toggle here. Okay, this is the operating point results toggle. So it's handy. Once you're done with the work, you can go ahead and turn that off. So from here, I'm going to show you how you can modify your own parts to use simulation. Because everything in the ngSpice simulation library that comes with Eagle is already mapped. You won't have to do anything special with those. So if you're just doing a basic simulation with resistors and capacitors and different sources, all of that's already catered for. But those parts don't have any type of PCB equivalent. They don't have physical components assigned to them. So when you're working with your own libraries, you can also attach SPICE information, and that way you can maintain your PCB, your PCB association. So I'm going to go ahead and open up.
So if I'm working on my own design, which is actually has a schematic and a circuit board, I can now assign the SPICE models to the components on my schematic. Is that what you mean?
Correct. So like if we look at this one here, you guys will notice that anybody who has used Eagle for any amount of time will recognize that these are standard Eagle components that come from the built-in libraries. Here's a resistor from the resistor library. We have an LED from the Lumined library. So these are all built-in libraries that come with Eagle that by default don't have any type of association. So what we're going to do is we're going to go ahead and associate them. So the first thing we want to do is you can associate them individually. So for example, I can click on the resistor. We'll notice that Eagle takes a guess at the SPICE type of device. In this case, it guessed correctly. It's a resistor. We can enter a value here, and we can say map. And right now, it knows that it's an intrinsic model. It's an intrinsic device, so it doesn't need any special outside model. And we just map the pins. A resistor is the same. It doesn't matter how you place it into the circuit. So I could have left it as is, but just for the sake of it looking nice, I'm going to make a match. Symbol pin 2 goes to model input 2. Symbol pin 1 goes to model input 1. Say OK. We get the check mark, and we say done. So that takes care of the resistor. Now, you don't have to do it on a one-by-one basis. We could go ahead and select everything. Select the model command. You'll see, do you want to convert all parts including ground and name to SPICE ground node 0? We're going to say yes. So basically what it's recognizing is that we have ground symbols in this design. And in SPICE, you need to define a node 0. You need to define where 0 volts is at, where 0 potential is at. So basically we're saying that these ground symbols are going to become that SPICE node 0. And that's generally what you want to do. So we'll say yes. And you'll notice that the grounds are already check marked. They're happy. And now let's look at the two remaining parts that haven't been mapped. So if we notice the LED, it guessed it to be an inductor, which is incorrect, but you can assign it whatever it needs to be. So we say diode. We go map. We're going to go ahead and find a model for it. You say load model. We go over to our 8.4.1 folder. Eagle already ships with several default models. We'll go into model. We'll pick DMod. It's a built-in diode model. You notice there are other models that ship with Eagle for different functions, for transformers, etc. So we will pick this one. At this point, you can choose to save it in the models directory or in the current directory if you want to include it with your project. By default, you can leave it in models directory, and it's basically going to overwrite it with itself. So we'll say OK. Yes. Verified. We go over here, and we can map the pins. We have the cathode and the anode. The anode will be positive. Cathode will be negative. And we will say OK. That part's perfect, and now we're missing our source. So it's been guessed to be an arbitrary source. For our purposes, it's an independent voltage source. Okay, so we can assign it a voltage. We'll say map. Again, because voltage is an intrinsic model, it's part of the SPICE language, we don't have to supply any type of independent model. And you'll notice that Eagle was smart enough to map the positive with the positive, negative with the negative. Say OK. And now what we're going to do is I'm going to say done for now. So far everything looks okay, but you notice that because we define this as a voltage source, this right now doesn't make any sense from a SPICE perspective. So one way you could do is you could use value and manually type in a SPICE string here. But that's not strictly necessary, and it can be complex depending on what you want that voltage source to do. So a better option is to pick the source setup command, which is this one over here. We click on the part, and we're going to get this dialog. So in this dialog, we can define our DC value, we can define our AC value, and we can define a transient function. Okay, so let's go ahead and define a sinusoidal function, offset 0. We're going to say its amplitude is going to be 1 volt. Should be fine. We're going to set its let's set it to 2 volts, just for. We're going to set its frequency to be 1 kilohertz with no delay and no phase. Okay, so we'll set that value. You notice that now the string changes. Now we have a complete string here. Now we go to simulate. We notice that simulation was happy. Actually, before I do that, let me make another change. Right here. Let's give these names so that they're easier to catch as probes. Yep. So we use the name command. We'll call this one out. We will call this one in. Let's do VN. Okay. And we can put probes if we want. That's what I'm going to do. I'm going to put a probe here. I'm going to put one here. Okay. So those are the two that we're going to go ahead and simulate. I'll put that over here. We'll pick a transient simulation. Let's start it at 5 milliseconds. And we'll pick the stop time to be 10 milliseconds. Okay, and you can notice we can put in all of the normal prefixes for the units. So we can use, as you can see, the different multipliers, the units. And this one should be ready to go. So we can hit simulate. Okay, 5 periods. So the period of this sinusoid is 1 millisecond. We have starting at 5 to 10 milliseconds. In general, the recommendation for these types of simulations, when you're doing a transient, you want to have an expectation of what you're looking for. So if you're doing a transient simulation and you know the input sine wave is at 1 kilohertz, that means the period of that wave is about 1 millisecond. So you want to try to have 5 periods in the simulation, because if you go for a really long time, so for example, if I put 100 milliseconds here, this is going to take a while to simulate. And what I'm going to have is a whole bunch of very, very compressed sinusoids that initially you won't really be able to tell what's there. You're going to have to zoom in. So if beforehand you just think about it a little bit and pick to have 5 periods or so show up in the simulation, you're not going to have to zoom in. So I'm going to leave it at 10. I'm going to say simulate. And there we are. 5 periods. So there's a lot going on here. We can again select our signals. We don't care right now to see a current. We do want to see the input and the output. So let's go ahead and apply changes. And here we can see what's going on. We have our input sinusoid. And then we see that it clips because of the diode. The diode only allows current to flow in one direction. So if I even turn off that one, let's go ahead and go over here. If I turn off the VN, you'll be able to see that the negative part of the waveform is perfectly preserved, but when we go on the positive waveform, it gets clipped because of the diode. Now, one other thing to show you guys, I'm going to go ahead and refresh, is that if you notice, this current here is from our independent voltage source, and it's automatically provided by default. You don't have to put a current probe on your voltage sources or on any of your independent sources. So as you can see, we got that one automatically for free, and we can go here to select signals. We can turn it off. We can see what our output waveform is. So we get some clipping thanks to that diode. Okay, again, feel free with any questions that you guys have to submit them through the chat. The two Eds are keeping an eye on those.
Now, I noticed that you use the models that came with Eagle for this scenario. Is there a possibility I could get model somewhere else, Jorge?
Yes, there is. So manufacturers will generally provide SPICE models for their devices. They have a very vested interest in making sure that engineers use their components in order to sell them. So they go through a lot of effort to make as accurate a model as they deem is going to be necessary. Now, word to the wise, depending on the type of simulation that you need to do, you may find that even manufacturer models don't cover all possible use cases. Again, the quality of your simulation is very much dependent on the models that you obtain. So keep that in mind if you're looking to do noise analysis, or if you want to see how parameters vary with temperature. You have to be really careful in making sure that the models account for that, because not all models do, and it's a lot of extra effort on the manufacturer side to incorporate those types of relations into the model. So just something to keep in mind. For 90% of the use cases, it's fine. But if you're doing anything special, you're going to have to be extra careful, making sure that the model contains and can represent the features of the circuit that you're interested in analyzing.
Now, you mentioned earlier today while you were doing the simulation that this was extremely useful for students.
Mm-hmm.
And I could see the benefit of actually doing the test virtually based on my textbooks. That way I could see my results in real time before going to the lab and running on an oscilloscope. Now, in a real case scenario, in a commercial environment, can you tell us a little bit about the benefits of having this SPICE simulation as well?
Yeah. So here's the important point to remember about simulation. You cannot go into a simulation blind. You need to have some idea of what you expect the design to do. The main benefits of simulation are, one, to prove your design concept, to be able to verify it before you invest in the actual silicon. So if you have no idea of what the circuit's going to do, you have no expectation of the result, then you're not verifying. You're not verifying that the performance of what you have designed is going to be what you expect it to be. You're just kind of flying by the seat of your pants and hoping everything works. And there are people who use simulation that way. And a lot of the analog greats frowned upon that. Bob Pease a lot of people thought Bob Pease, for example, was against SPICE, and he wasn't. There's very documented cases of him using it and using it well. So he knew how to use SPICE. He was aware of the benefits of the tool. What he was against was people using it blindly. So for a commercial environment, the main benefit of simulation is to, before you commit to hardware, before you commit to spending the money on your PCBs, you can gain some confidence knowing that from the simulation standpoint, from the theoretical standpoint, everything is sound and should work. And that's the main benefit in a commercial setting. You can test ideas, you can make sure that your intuition and your design intent is in line with what you should expect from physics. Also, by having an idea, by having a notion of what the circuits should do, you'll be able to notice if anything goes wrong in the simulation. If you're flying blind, you're going to take whatever comes out of that simulation as truth. And if you don't set up your parameters correctly, if you're not aware of the limitations of a SPICE simulation of your models, then you may be very easily led astray. So in a commercial environment, that's what's important. You need to have some idea of what the circuit's going to do, and you're using the simulation to verify your design intent.
Excellent. Thanks, Jorge.
So a good example of that is, for example, in transistor amplifiers, where gain varies widely. A simulation may help you see the limits of your design. Another example where you can run into an issue, and I'm going to go ahead and show it for the other simulation type we want to show. Let me go ahead and close this. Let's go over here to the op-amp schematic. Okay. So this is using Eagle's built-in, the basic op-amp model that we're shipping with. Okay, so that's what we're seeing here. We have two Vouts. I'm going to go ahead and get rid of them. Get rid of one of them. Okay. Now here's a classic example. The most basic op-amp model doesn't take into account a signal hitting the voltage rails, the voltage limits of an op-amp. The most basic one. So it assumes that the op-amp can be linear as to whatever voltage the gain sets it to be. So for example, if we set this to 1,000 gain and we put in 1 volt, 1,000 times 1 is 1,000 volts. And the most basic, again, I need to emphasize that the most fundamental SPICE op-amp model doesn't take into account that effect of hitting the rails. So you'll see an output of 1,000 volts, and if you have zero concept of what your circuit should be doing, that should raise a red flag, because in reality there's no op-amp with normal, plus minus 12 volt rails that can hit 1,000 volts on the output. So those are things that you need. That's why it's so critical to have some concept of what the circuit should do. That way, if the simulation gives you a result that you find odd, you can investigate and fix it. So the best thing to do, and the best recommendation is these models are nice because they're already there, but you don't want to sign off on your final design relying on them. The best thing to do is to go to the manufacturer and find the model for your op-amp. Verify what the model is good for, what effects it does simulate, and most manufacturers are really good about this. In the comments of the model, they will actually show what the model can simulate. And actually, I had one open. Let me go ahead and show you guys one. So this is a model from National Semiconductor, and this model is for an operational transconductance amplifier. Okay, and if you notice here in the features section, it actually tells you what the model can cover. So we can see here the features of the chip itself. Its gain is adjustable over 6 decades, good linearity, linearizing diodes, noise supply range. Now note, this model is single pole in nature and overestimates AC bandwidth and phase margin by over 2 times. Although refinement may be possible in the future, please use bench testing to finalize AC circuit design. So right now, right off the get-go, you know that if you're doing an AC sweep to check the bandwidth of this amplifier, you're being told right up front, this model is going to overestimate that. So now you know something to be aware of in the simulation. So good manufacturers and most manufacturers will take the time to document some of the limitations of the model, what it does include, what it doesn't. For example, if we look at this one, we see that it includes the offset current source over here, and we have a few other things, but we don't see any options for noise analysis. We also don't see any type of setup for, I turned that off, any type of setup for thermal simulation as well. We don't see any type of consideration given for parameter variation relative to temperature. So those are limitations of this model that if you're going to use it for those things, you have to be aware of. So keep that in mind when you get models from the manufacturer. So let's look at this one here. We're going to do an AC sweep simulation on this one. So I'm going to click over here. Again, instead of for AC sweep, we have decade, start frequency, end frequency. We can also do a linear type simulation. So we're going to go ahead and hit simulate. So we're starting from 1 hertz all the way to 10 megahertz. So it's a very wide frequency sweep. I'm going to click simulate. And here we are. And you'll notice again, all the voltage sources, their currents automatically come in. We can go to select signals. We can show them. For our purposes, we don't need them. These off. Oh no, we do need this one. There's so many, it's easy to figure out which one I'm interested in. So apply changes, and here we can see. So the first one is the op-amp without any form of filtering. So it's just a normal inverting op-amp, and its model shows that that it does at a certain frequency start to roll off. As we know, op-amps in the real world do have a limited bandwidth, which is related to the gain bandwidth product. in the case of the second op-amp, we're seeing the filter response because the second op-amp, as we can see over here, is a second-order low-pass filter. And that's what we're seeing right here. Okay, so everything looks good. It rolls off pretty well. But we also notice that at some point, because of parasitics, it doesn't monotonically continue to attenuate higher frequencies for all frequencies. There's a point where, because of parasitics, it starts to back up. Okay, so you know that if you need constant attenuation, it's really only good up until about 350 kilohertz or so. Okay, so up till there, you're getting monotonically increasing attenuation. Sorry. Okay, so we've already shown how we can do the mappings. We've shown the different types of simulation. We've covered what the use of simulation is. The last thing I guess I want to show you guys is that you can assign models in the library, similarly to how we did it in the schematic using the add model command. In the library, you can assign models. So I'm going to go ahead and open up a library. Go over here.
So in your opinion, Jorge, should we recommend the users to do their mapping on the library when they're building the parts, or do it directly on the schematic? Do you have a preference on that?
I think for personal designs, and if this is what you do day in and day out, it's better to do it in a library. So I would recommend doing it in the library. That way, whenever you use that part, it's already set to go. The schematic assignment is useful if you're just quickly prototyping something, or you just want to do something quick. Then on the schematic, you can do the assignment. But most of the time, for most use cases, the library would be the best option.
Excellent. Okay.
Okay. So over here, I have this transistor. And all the simulation assignment is done in the device. Okay, so we go to the device, and you notice that now we have this new icon over here, Add Model. Pick it. We're going to say what type of part this is. This is a field effect transistor, a MOSFET. I'm going to say Map. I'm going to go ahead and go to Load Model. And for me, it's this one over here. Say Open. Okay. So one thing that, I exited it, I think, accidentally. Whoa, what happened there? Got stuck. I did get stuck. So one thing that was brought to my attention is that if you have a library model defined already, if you have a model defined in the library, and for whatever reason in your schematic you need to override it, you can do it. The schematic assignment will override the library for that particular design. So that way, if you're using something from a managed library, for example, and you don't have access to the original managed library, you can still include your own models on the schematic. So that's a good point to mention. I think I'm going to have to close Eagle, because it got thrown behind.
So the model itself, the model, the SPICE model, is actually in the schematic file. It's not calling out a third file, Jorge. Is it actually in the XML?
Correct. Correct. In all of these cases, the model gets embedded into the design.
So if I email the schematic file to somebody, it will carry the simulation models with it?
Correct. I mean, the model is in its own model file, but the XML will call to it.
Okay.
You can also have the models in the models directory. Okay, there we go. In the library, though, when you do that association, the model is part of the library. It is included as part of it, so you no longer need the separate file. Let me go ahead and open that up again. Okay, let's go back to our library. I can stay offline a little bit longer. Here we are. Okay, so I'll pick this one. I'll pick the mapping again. MOSFET, map. And now in this one we pick load model. Again, you'll notice we have the information here. We can find, like I said, documented, some default things that they include. If there's any limitation of the model, so for example here, the voltage-dependent capacitances are not included in this model. So that's something you have to take into account if that's important for your simulation. You'll notice that inside the library, these save-in options are grayed out because you're not saving to any specific location. It's actually becoming embedded in the library file. So there's nothing else to do there. So we say OK. This model card cannot. What happened here?
It's a sub-circuit.
Yeah, not a model card. Doesn't let me change it. I remember I fixed it in another design, so let me go ahead and show that one. So I'll cancel this. But that would be the procedure. Where is it? Where is it? Here we go. Okay, so in this one, let me see what it ended up doing here.
Can you guys hear me?
This one has it. Yeah, I can hear you, Ed. You're in.
Oh, I was just going to say so you chose MOSFET, so that means you have to include a model card, not a sub-circuit.
I should
so
have
the file you had was a
yeah.
sub-circuit, so you can certainly redo it and choose sub-circuit.
That's what it was.
Thanks, Ed. Appreciate that.
So pick this one. That was my mistake, so I apologize on that. And now it'll be happy. Because now we have a sub-circuit, we say OK. File saved and verified. And now you can just adjust. Node 1 is the drain. So you got to make this one 1. 2 is the gate. So that part's OK. Source is the third one, so we say OK. And now it's done. There we go. Thanks, Ed. Thanks for that clarification. Okay, so that pretty much brings us to the end of our webinar. If there's any questions, please feel free to let us know. I'm going to go ahead and stop sharing now, and I'm going to kick it back to Ed.
Greatly appreciate everybody attending the webinar and joining us today. We're going to be hosting a new webinar on the same topic again. Sometime in at the beginning of December, we're going to go review about the simulation all over again.
Ed,
we're going to review about the simulation all over again. I did?
Yeah. No, you're okay now. Go ahead and talk.
Oh, that's weird. Okay. So, if there's any questions, go ahead and put it on the chat group. I think we're way over what we expected to be, so I don't really want to overextend this. And this is our first webinar about simulation. Please get some more information on our Autodesk Eagle YouTube channel. We have a series there of Jorge divided it in 3 sections. Each one is approximately 5 to 6 minutes each, and it kind of reviews this information that he did today as well. So, and we'll post this recording as soon as we have it available. Thanks again for joining us. Greatly appreciate it, everybody. And I don't see any questions, so well, have a great day.
Good day, everybody.
Thank you. Bye.